Anyway, happy Halloween, happy Friday. Okay. Today, talking about exponential functions. Okay, so after we're done with this, we have enough foundation, we have enough knowledge to start talking about what the word log means and different things like that. So we're going to graph exponential functions, just talk about some of the properties just real quickly. Evaluate exponential functions with base e, so I'll talk about what e means. Use them to compute compound interest, and we'll talk about like something that continuously compounds infinitely. And in the last part, using some applications. Okay? So first we're going to talk about what is an exponential function. That'd be a good start to it. Exponential function is recognized as a function with a constant base, which has to be positive and not equal to 1. With a variable exponent x. And let me go ahead and underline constant base, because that's important. You can't have a base that's changing as you're plugging values in, because then you don't really have much of a graph. But that's how we define it. And let me give you some examples underneath it. So here's some examples of an exponential function. You could have f of x equals 3 to the x, g of x equals 1/3 of the x. You can even do h of x equals the square root of 2 to the x. Okay, square root of 2 is still constant, even if it doesn't end. It's kind of ugly to do some of those, but we'll talk about that a little later. And then non-exponential functions. Okay, so some examples would be m of x equals x squared. Now you might think, well, that kind of looks like an exponential, but the base isn't a constant. The base is a variable. Okay, so therefore non-exponential. N of x, negative 1/3 of the x. So again, it's not positive. Okay, so we won't say that it is exponential. The reason for that is because the values are going to change when it's negative, right? And your answer might be negative, might be positive. So it's going to keep alternating back and forth with even and odd powers. And then p of x equals 1 to the x, because that's just going to be a constant, right? 1 to the 100th power is still going to be 1. So nothing exponential about it. Okay? Now, I'll just put here real quick, so the main reason as to why a base is not negative, okay, is to avoid a situation where, for example, negative 4 to the x. So if x was a half, we will not have a real number, which, no bueno, okay? So that's one of the main reasons why you don't want to have a negative, besides just alternating between values, being positive and negative. If it was a half, you get a square root, and that's not a real number. So we try to avoid those as much as possible. Okay? All right, let's graph them. So example, let's graph the following. So part A, we're going to graph f of x equals 3 to the x. And then part B, we're going to graph g of x equals 1/3 of the x. Okay. observe some properties, like just some characteristics when we graph it. So underneath here, I'm going to put a little XY table. Okay. Kind of made that too big. Oops. Oh well. And the numbers are going to plug in, be from -3. I want one more to 3. Just to save a little time. I mean, I'm not going to plug each one in and simplify, but if I were to plug those in for x, I would get the following values. So 0.04, 0.11, 0.33, 1, 3, 9, and 27. Look at the behavior of it. Before I even graph it, we could see that with the negative numbers, if I keep going into the negative direction, this gets closer to 0, right? Okay, so it's kind of like that asymptote feeling, right? It's getting close to the x-axis, but not going to cross it, because could you ever have this equal to 0? No, right? There's no x value that makes that whole thing 0. So in that case, my x-axis would be like a horizontal asymptote. And on this direction, when we go positive, it just keeps going, up forever, pretty fast actually. Okay, and then right here in the middle, I'll just put a little note. That's our y-intercept, right? So it's going to hit the y-axis at 1. So let's go ahead and just draw that. And just for all intents and purposes, we're just going to draw a rough graph. The one thing I want to put up here is definitely this point. Okay, that's where it hits the y-axis. And then we said that it gets closer to the x-axis where it's negative, and then when it's positive, it just increases exponentially. So there's our graph. Okay. Now, for this guy over here, we'll do the same thing. Let's see if I can fit the table. 3, 2, 1, 0, 1, 2, 3. Same values. Okay. Now, with negatives, think about something for a moment. When you have a negative exponent, what does it do to the value? It's going to flip it, right? So it's going to be what? The opposite of this behavior? That's what we're going to see. So the negatives are actually going to make it larger, and the positive numbers will make this smaller. Okay? So it literally just flips it. Just like that. But the y-intercept stayed the same. That didn't change. So it's still going to hit the y-axis at the same spot. So just drawing a little graph underneath it. Just like before, I'm just going to do a rough sketch. But I still want to make sure the y-intercept is graphed correctly. Okay? And it's going to be, what, the reverse of this guy in a way, huh? So it's going to be getting larger really fast, and then it just gets closer and closer to the x-axis, but it does not cross it. Because again, there's no number I could plug in to make it 0. Okay? So, what do you think? Any questions on those two graphs? Not too bad, huh? Let's just put here at the very bottom some of the things I just mentioned. So, first thing we want to note is that our HA is the x-axis. Okay? And that's just for right now. We could do some transformations to where it changes, but for just the generic exponential graph, it is the x-axis. Okay? And if it's the same base but just reciprocated, then couldn't we call this a reflection across the y-axis? Right? Is that what's happening here? So with something like this, when you have a 3 to the x and a 1/3 to the x, okay, it's the same graph, but it's a reflection across the y-axis. Just a couple little notes there, just some observations. All right, let's talk about some properties. Properties of the graph. F of x equals b of x. So now that we've seen a couple of them graphed, let's see if we can't finalize some observations here and talk about it. So our first little property, if my base is bigger than 1, so I'm talking like part A over there, oops, f is an increasing exponential function, sometimes called an exponential growth function. Which makes sense. I mean, if you look at it, it is growing positively forever. As I keep plugging more x values in, it's climbing to those higher numbers really fast. So if you want to put in parentheses, look at example part A. Okay, that's what that's describing as. So now let's talk about part B's characteristics here. So if B is a fraction, then we say f is a decreasing exponential function. And this is sometimes called an exponential decay function. Okay. Oh, I'm gonna use the same color. Hold on. Let's change that. There we go. Okay. And we'll just say, look at example part B. Okay, so we just did one of those. We'll do an application problem of a decay function. We'll go into chemistry a little bit and talk about some of those. Okay? So far, so good with that? Now, we got some names. We described a little bit of behavior. Let's talk about some domains and ranges now, right? So looking at those two graphs. So the good news is the domain, well, there's no restrictions, right? If we're following what an exponential function should be, using the definition, then I can plug any number I want in there, okay? So all real numbers. Next, the range, okay? Well, is it ever gonna be 0? No, we said that, right? But it's gonna be every number beyond 0. So it'd be 0 to infinity. Next, kind of like what I wrote down there, the line y equals 0 is the horizontal asymptote. And the last little property we could talk about, the function passes through the point 0, 1 because, bless you, b to the 0 power is 1. Just using our exponential rules there. Well, not exponential rules, exponent rules, I should say. Okay? And these facts you can get from looking at both graphs, right? It's nothing, not like a revelation of any kind. The only thing that would be new to you guys is just hearing these two terms right here. All right? Now, let's take these functions and use some transformations. We're going to shift them around a little bit, do a little bit of moving. So let's try that out. Okay. So for example, let's graph f of x equals 2x minus 1 plus 2. Make that more clear. There we go. So our rules for transformations, they work for exponents too, which is awesome, okay? It's not like there's a special set of rules for doing these, it just kind of matches it. So first, let's list the transformations. Now notice, this -1 is in the function, right? So there's a horizontal movement happening. So if it's a -1, what direction is it going to go in? To the right, by how many? Just 1. Okay, so this is going to shift to the right 1 unit. Okay? So with that? All right, next. The +2. It's on the outside, right? There's a vertical movement. So am I going to go up or down? I'm going to go up. So I'm going to shift up 2 units. Okay. I'm going to draw the graph with those characteristics, okay? I'm not going to worry too much about accuracy, like plotting additional points. I just want to make sure when I'm done graphing it, these are the things that we see, okay? That's all I want to really focus on. Alrighty, so let's do that. Let me use this example right here to talk it out, okay? So what I do typically when I do these transformations, I look at the y-intercept to help me out. So I'm moving it to the right 1. So this point is going to move over here, right? And then I'm going to move it what? Up 2, right? So up 1, 2. So this point is now over here, which is what? 1, 3. Does that make sense? Okay. So at 1, 3, okay, that is the sweet spot. That's where it's going to what? Curve. That's when it starts turning. Does that make sense? Okay. So let's do that. And my y-intercept, let's think about where that's going to be now. Okay. So where's it going to hit the y-axis? So if I plug 0 into here, okay, 0 minus 1 gives us what? Negative 1. So what would 2 to the negative 1? What's that number? It's a half. Yeah, it's a half, right?
Oh.
And then plus 2, 2.5. So right here is where it's going to hit the y-axis. Okay. So I'm going to go ahead and draw it. But at this point, because that's what it originally was, right? That's where it hits the y-axis at. But at that point is when it's going to start curving up. And there we go. Now, it's kind of weird over here, right? Like, does it level off? It does, okay? Our original HA was the x-axis, right? Well, because we shifted it up to, well, my HA also shifts up too. So this is going to approach 2, but it's never going to hit it. Okay? So here's what I would, well, let's put a little note here. So this is going to move our HA by 2. So my HA is now going to be y equals 2. So anything, if you do a vertical shift, whether it's up or down, that's going to shift your HA. Okay? But when it comes to graphing this, again, we know it's going to hit the y-axis at 1. So figure out where that 1's moving to in terms of the transformations, and then go ahead and graph your function. All right. Questions? So that takes care of graphing exponentials. Okay? Let's talk about this E guy. All right? The number E. My favorite number. The number that doesn't get a lot of credit. We have Pi Day. We should have E Day.
Oh, we're talking about E already.
Okay. So let's talk about evaluate question. The exponential function that has a base of E. Let's consider the expression 1 plus 1 over x raised to the x power. Okay? So let's consider that expression for a moment. It's an interesting expression. In fact, that has a financial connection to it, which we'll see a little bit later. So here's what I'm going to propose. As x goes to infinity, the expression will approach a constant value we call E. So, in other words, if I keep plugging numbers in for x, like 10, 100, 1,000, 1,000,000, it's going to approach a number that we call E. And here's what it looks like. So I'm going to put an XY table down here. so you can see it. All right, so I'm going to show you, as I'm plugging numbers in, what this gets closer and closer to. Okay, so if I plug 100 in there, you get 2.70481. It keeps going, by the way. I'll put dots. Okay, it does keep going. I just kind of cut it off there. Now I'm going to plug in 1,000. You get 2.71692, and again, it keeps going. So it did change a little bit, huh? Okay, next, I'm going to plug in 10,000. So 2.71815, dot, 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 dot. So the change got a little bit smaller now, right? Not by much, but it gets smaller now. So that means we're getting closer to a number that it's approaching to. Let's plug in 100,000. So we get 2.71827. So notice that only those two digits at the very end started changing. So we're getting closer. Let's plug 1,000,000 in. So if we plug 1,000,000 in there, we get 2.71828. Let's plug 1,000,000,000. Can I fit that on the board? We're going to try it. Okay, we get 2.71828 again. It's just some of these digits, a little bit of a difference, but not much. But we can see that it's kind of stopping right here. Okay, those are our digits right there. That, and again, it does go on forever. I just stopped at those places there. But that's what we call the number E. Okay? So the number E comes from this expression. And as you keep plugging in larger and larger numbers, it gets closer to that value. Okay? So let me just write this up here. So E is approximately 2.718281828. But you're not going to use all those digits when you do it. In fact, what's nice is that your graphing calculators have it on there, okay? So you don't have to worry. Typically, when I use it, if I was doing it by hand, I just stop at 2.718 and just call it a day. So what do you think? February 7th? Making a math holiday? I think it'd be fun. Let's talk about all kinds of stuff we can do with E. Now, a couple facts with this, okay? And I'm gonna give you a little history as well. So just some basic stuff, and then we'll use it in some calculations, okay? So the first thing, the value of E, which you can probably figure out, is an irrational number. There's no pattern to it, okay? It just keeps going on forever, just like pi. The function f of x equals e to the x is called the exponential function base e, or the natural exponential function. Okay, so let me just underline those. So if you have a function that's e to the x, sometimes it's called the exponential function base e, or the natural exponential. The word natural is kind of weird, because if you're looking at that equation I wrote up there, like, what's natural about that? Does it just magically come up in situations? It does, and we're going to see it. Because again, that's not a function that comes off the top of your brain when you learned about all those years of algebra and stuff. But yeah, the word natural is because it naturally comes up in problems and applications. Okay? All right. So let me just put a little history, some history notes over here. And then let's look at some examples. We don't really spend a lot of time on history and math stuff, which is kind of unfortunate. There's some really cool information there. So that's why I want to just give you some highlights, that's all. So the history of E. Okay? So the first person we want to tip our hat off to was John Napier. So 1550 to 1617. Okay? So he made the first indirect appearance. Okay. So the first indirect appearance of this concept, meaning that he didn't really call it E. He was trying to kind of work through something called logarithms, which we're going to get to, but he was the one who defined logarithms through a process called dynamical analogy. Okay, so essentially he was trying to find a new way to do addition and multiplication. And he created logs by doing this, and then inadvertently he actually started talking about this number through logarithms, which is kind of cool. Okay? The model that he created is almost equivalent to what we call a log in today's standards, which is y equals log base b to the x if b to the y equals x. This will make more sense in the next lesson, okay? So again, just a little historical marker there. So again, he was like just having fun with it. He was just coming up with different ways addition and multiplication could be done, especially when it comes to exponents. And he came up with some logarithm stuff. And what we did today is we kind of refined it a little bit further and defined it like this. Okay, then the torch got passed off. There was a direct appearance of this 100 years later. By Gottfried Leibniz. These names, I tell you what. And his birthday, let's see, it's 1646 to 1760. Okay? He's huge in the calc community. So he picked up the torch from this. Okay? So in his work, when he was dealing with calculus, so we'll put here, in his work with calculus, okay, he identified E as a constant. But he labeled it B. So E didn't come up yet. So he came up with this value. He's like, hey, this is pretty special. He was working with it, but he didn't call it E, he called it B. There's nothing wrong with that, but B's are everywhere in mathematics. So B might not be the best. So who was the one who came up with the actual letter E? Well, Leonard Euler. He gave the constant the letter E. Maybe because his last name has an E in it. Imagine that, okay? And he went even further. Oh, wow, that's the word constant. My brain just got rid of the T. That's weird. But anyway, he took the range even further. He created a bunch of things with E. Okay? Well, I'll just give you a couple of formulas that he discovered with it. Okay? Jeez. There we go. Oh, man, I can't write. There we go. So these are two famous formulas that he was famous for. Okay, e to the I theta. I is an imaginary number. Remember i's from a long time ago? So if you raise this exponent to an imaginary number times the angle that you're looking at here, it's the same thing as cosine of theta plus I sine of theta, and then e to the I pi plus 1 equals 0. Now, again, that doesn't mean too much to you guys at all, but if you ever see those formulas, okay, it's this guy right here. He was the one who created them, and he did it based off of the prior experience of other people when it came to this. So a little bit of a history lesson, but a cool history lesson, I think. So let me just go ahead and graph that function over here so you can kind of see it in action. And then let's use it for compound interest. Which that sounds weird, but you're going to see it. So here we go. We're going to graph f of x equals e of x. Okay? And again, I'll show you tomorrow on the graphic calculator where it's located. Okay, it's there. It's not too hidden, but it is there. Let's just do a little XY table. Now, because this is matching, and I erased it already, but this is matching our first property, right? It's bigger than 1, e. So it's going to look something like this, right? It's going to go up into the first quadrant infinitely. So I'll do the same thing. -3, -2, 1, 0, 1, 2, and 3. Small little XY table will just be plugging numbers into it. And then the graph underneath, I'll stay consistent. I'll plot the y-intercept, and then the rest of it I'll just show the behavior. So there's the y-intercept, and there we go. So it looks like any normal exponential function. It's going to follow very similar patterns to it. And the good news is that if you had transformations, like if you had a -1 and +2, it's going to match just what you did with the other exponentials with its transformations, which is perfect. Nothing sucks more when you have a new concept of math that doesn't follow what the other stuff does. So this does follow those steps. Okay, so that's what E is. Let's see it actually being used, and what we're going to call compound interest. Okay, so first up, if you hear the word simple interest, okay, is interest computed on the principal principal amount vested. So let's say you invested $5,000 in something, and the interest rate was 4%, okay? So you would take the 4% on what you invested and come up with what your account balance would be afterwards, given some amount of time that has occurred. Now, compound has more steps involved. Compound interest is interest computed on both the original principal, so what you started with, and on the interest already accrued. This is where loans kind of kill people, especially student loans. Not fun times, I will say, with student loans. So what does that mean? Let's say you invested $5,000 again, right? And it's accruing interest every day. So what this says is, like, let's say a quarter way through the year, whatever interest you accrued gets added to your principal, okay? So the next quarter of the year, when you're accruing interest, it's accruing interest off of what you had originally and the first quarter of the year's interest on top of it. So that's a bad thing for a loan, but a good thing if you're investing, okay? That's what compound interest is. So let's get a little, let's figure out some of these formulas here. So suppose that interest is compounded annually, which means yearly, by the way. An investment of $P. We're trying to make it generic. So let's say you invested a P number of dollars into some account, okay? And we're gonna do it at an annual interest rate, we'll call R, for T years. Okay? So just a nice little hypothetical. Let's say you had just an amount in an account, we'll call it just P. And your interest rate is R, and T is the number of years you're going to keep it into that account. Okay? Then, the amount we'll call A in dollars is computed as follows. Okay? So there's my setup. Now let's talk about it. So year one. Okay, so how much are you earning after year one in that account? Well, this is how you calculate it. So your account balance, you have your initial principal balance, what you started with, and you're going to add the interest. Okay, how much interest did you earn? I think that's pretty easy to figure out, right? It's just what you started with plus the interest. Okay. So what does that look like as a formula? So A equals P is what I started with plus the principal times my interest rate. Right? That's all I'm doing. Now I could simplify that a little further. Let's do that. I could take a P out of both terms. So I could do P times 1 plus R. Just makes it a little easier to work with. So there's nothing wrong with this. It's just easier to work with it when you factor a P out of both terms. So that's after year one. That's how much you're earning in this account. Let's look at year two. Okay. So what's your balance going to look like? Well, you're going to have your year one balance. So we're going to take, what did you earn here? Okay. So that's what you're going to start with in year two. And then you're going to add the interest that you earned in year two on your year one balance. Okay? So if I'm investing it every single year, you just, whatever you started with, you add more to it. Next year, whatever you had then, add more to it. So let's go ahead and write the formula down for that. So this is going to be A equals. Now, what did we start with? It's this guy, huh? That's what this is. So we started with, that is my year one balance. I don't know if you want to color code, you can. So that's my year one balance. Now, the interest that I earned, I take this and multiply it by R. Just like what I did up here, right? What I started with, my interest is principal times rate. This is what I started with, so it'd be this times R. So it's going to look like this. So P, 1 plus R times R. Now again, there's nothing wrong with that formula, but let's simplify it up a little bit. I'm going to factor, see how they both have a P, 1 plus R for both terms? I'm going to factor that out of both. Okay, so this is going to be P, 1 plus R, and then what's left? Well, 1 plus R. If I factor this out of the first term, it's just a 1. Factor this out of the second term, I just get an R, so it's just 1 plus R. And then because I did that, I can combine it with an exponent. So that's what my balance will be at the end of year 2. Now, before I go to year 3, because after year 3 I'm done, you're going to see the pattern. See how I still have this as like a base in a way, right? And the only thing that changed is what? The exponent. So can we imagine that year 3 would be like the same thing but a third up here, right? Okay, kind of seeing the trend of this. So the third year, I'll still write this down. So you're going to take your year 2 balance, I'm going to abbreviate that, and then add interest onto it. So interest on your year 2. Now, I don't know if I'm going to have space. I'm going to write it underneath there. I don't want to squish it all. Okay, so my year 2 balance was this guy. So let me bring it over. And then just like the other pattern, to find the interest, I take this guy and multiply it by the R. Okay, so I'm gonna need parentheses though. So I'm gonna put parentheses around it, put R, make it a little bit easier. Now, just like the trick up here, I'm gonna factor a P 1 plus R squared now, because they both have that. So it'll be P 1 plus R squared plus, and then this will just be 1 plus R, because that's just a 1 that's there, just an R that's left. And then I can go ahead and combine those. Oh, not plus, I'm sorry. It's multiplied now. And I can combine those with the next exponent, R to the third. So kind of like what I already set up here, right? We kind of expected that. Okay. So to find compound interest, I think we can come up with a formula pretty nicely, huh? So my interest formula, so compound interest formula. Hello? Okay, thanks, bye. Thank you. You need to go to the cafeteria. No clue why. Just the messenger. Okay, so compound interest is going to be the account balance equals principal, 1 plus R, and then T, right? It's whatever year you're at, that's what you put there. There we go. Okay. Now, again, I just showed you where this formula came from, that's all. You know, that was me deriving it. I didn't want to just give you the formula and not explain like where this came from. Okay? All right, so far so good with that? I appreciate you hanging in there. I do. Okay, now, what if we did something crazy stupid? What if we, compounded more than just once a year? What if we did like 4 times a year, right? Or 12 times a year, okay? Bless you. What would we do to that formula, okay? So it's actually pretty simple. So let me just put here, okay, now let's increase how frequently interest is compounded. Okay? This was just a year, right? At the end of the year, you take your interest and put on your principal. What if I did that more than once a year? Okay? So here's the deal. Each compounding period, okay, represents a fraction of a year, and the interest rate is scaled accordingly. So if for each compounding period, we're going to say as 1 over n. Okay, so if you're compounding 4 times a year, then it's a 4th each time. Times my interest rate is how they calculate it, so it's just r over n. Okay, so if you're doing more than just a yearly compound interest, and you're doing it like 4 times a year, 5 times, whatever, you take your interest and divide it by n, okay? So it's being scaled accordingly. So that formula over there, we can now replace it with those variables. So it'll be p times 1 plus r over n, and up here it'll be n times t. N being the number of times you're compounding it in those years. Okay? So if you're doing a 4-year investment and you're doing it 4 times a year, you're compounding interest, and you're going to do that whole thing 16 times. So that's why it's n times t. Okay? So there's our compound interest formula when you're doing it more than once. Now, by the way, this works if you're just doing it one time. Okay? There's nothing wrong with that. If you're doing it just once, this is just r over 1, which is r, and 1 times c, which is t. Okay? So that's the formula we're going to be using. All right. So far, so good? All right. You guys are doing great. So now the last thing I gotta show you, and then we jump into the examples. And I only have 2 examples, and that's it. It just takes a little while to build up to it. Again, I want to show you where these come from. I don't want to just randomly throw things at you. So the last thing I want to do is incorporate e in this. Okay. What if I compounded infinitely, like 400 times a year, 500 times a year? Just keep going infinitely. Okay. Well, if you remember what we did last lesson, if n keeps getting larger and larger, won't this whole thing approach 0? Remember how we talked about that? So this is just a 1 here. But then this goes to infinity, right? So p to infinity, we really can't figure out what's going on there. So if I want to continually compound forever, this is not a good formula for it, okay? But here's what we could do. This guy right here is e, right? Didn't we just say as this gets larger and larger, it approaches a number, right? So can we fit this into here somehow to where if I do this infinitely, it's going to make sense to us? And we can, okay? So here's what we're going to do. We're going to make some substitutions here to create a new formula. So what if we compound infinitely? That's the question now. And we're going to use our old buddy, e to do it, okay? So now, let's assume we compute, okay, interest continuously. That is, n goes to infinity, okay? So here's what we're going to do. We're going to take our normal formula, and we're going to make a substitution, okay? And here's what we're going to substitute, okay? So I want to put x in there, right? That's what I want to try and figure out. So let me just make a little side note here. So if I let 1 over x equal this fraction, r over n, because I want to replace that with 1 over x, right? Because we know it works. Man, people don't want me to teach that. Take that back. There's a student coming in. That's good. I had an administrator pop in randomly. It's like, can you please go? I want to talk to you. So if I want to substitute 1 over x for r over n, okay, if I just cross multiply these, wouldn't we get, I'll put underneath here, n equals xr, right? So let me go ahead and make that substitution up here. So we get p times 1 plus r over xr, and up here would be xrt. Okay. So far so good. So now these r's cancel, huh? So I'm left with, I don't want to, are we okay if I just write underneath here? I know that doesn't flow well. I'll put it underneath here. So a is equal to p, 1 plus 1 over x, and then x, r, and t. So that's kind of looking like our e formula, right? We're getting closer. Now I'm going to use a property of exponents to see if I can't clean this up a little bit. So we get p, and then 1 plus 1 over x. And then what I'm going to do next is raise that to the x power, and raise this whole thing to rt. Okay, and I'm sorry, p's not part of it. P's on the outside. There we go. Okay, because if you remember your rules of exponents, power to power you multiply. So I do get the original. I didn't change nothing. So now we know what this is, right? As x goes to infinity, that whole thing goes to e, huh? So now it's a equals p times e to the rt. Okay? So if you're going to infinity, just keep compounding interest like that, you're going to use this guy to figure it out. I don't know, when I was first shown this, I was amazed by it. I mean, that is really cool. So remember when I said it's a natural number? That's why it's called a natural number, because it does pop up naturally in certain places. Okay? And this is just one of those in finances. So let's try, yeah, we're actually doing pretty good, believe it or not. Let's go ahead and try an example. So I got 2 examples to do, and we are done. Okay. It just took a while to explain where these formulas came from, that's all. So suppose 4,000 is invested and it pays 10% per year. That's pretty good. Under the following compound options. Okay, and what we're going to do is we're going to determine the total amount after 5 years. Okay, so we're going to compound it annually, quarterly, and then continuously. And after 5 years, we're going to see which one has the most money. Okay. There we go. Now, ooh, yay! I got both of them up here. I always have a bad habit of erasing things that I would like to have on the board. So we're going to use those two formulas, okay, to figure this out. So annually, that would be 1, right? 1 time a year. So n's 1. I'm going to go ahead and plug everything in there. So my principal is 4,000. So account balance would be 4,000. 1 plus my interest rate is 10%. Okay, so it'd be 0.10 over 1, because that's my number of times I'm compounding it just once a year. And then 1 time a year times, well, I'm doing this in 5 years, so 1 times 5. So we get $6,442.04. Okay, next one, quarterly. Well, that means 4. So 4 times a year, you're going to compound this. So my account balance would be 4,000. 1 plus my 10% over 4. And this time, it's going to be 4 times 5. So multiply everything together. I get 6,554.47. So that kind of makes sense, because if you're compounding more, then your interest is being calculated off of a larger amount each time, which is good. Now, continuously, well, it's not being compounded, any sort of amount. It's just continually adding more and more each and every second. So we're going to use that formula down here. So that's 4,000 times E. My interest rate is 0.10, and the time would be 5 years. So then we get 6,594.89. Now, it's kind of weird. You're thinking, well, at least I thought about this when I first was learning it, is why do you want to continuously compound it infinitely? Well, here's the reason. This is my ceiling approach, right? Remember how I said things get closer to a number but doesn't hit it? That's what this is, okay? So no matter what you have for a $4,000 investment for 10%, you're approaching this number. You're not going to get past that number, okay? Unless you add more to it, more than 4,000 to start, or you increase the interest rate. So that's why we do something like this, to analyze where's that ceiling hitting it, okay? All right, we got the last one. Are you okay if we extend 2 or 3 minutes after the bell, just to finish it? I promise it won't be long, okay? You're probably thinking, yeah, right. No, I'm being serious. It's not gonna be long. I wanna do one extra problem, and it's just half-lives. If you're in chemistry, you'll probably talk about this, or even biology, you talk about half-lives. So, it says here.
Pardon the interruption, but I would like to announce the door winner. And I appreciate all the votes that came through. The winner of this year's door decorating contest is Shut Down Drugs Before They Shut Down Your Future. Congratulations, and I'll be bringing the treats on Monday.
Okay, so the half-life of tritium, I know I'm butchering that one. It's a radioactive isotope of hydrogen, okay? Is 12.32 years. So what that means is this: after 12.32 years, you have half the radioactive substance in that element, okay? That's what half-lives are. Now, the formula which you're gonna need. So the formula for half-life, and this is for any element that exists, okay? Any element has the following. So it's gonna be n sub 0 half raised to the t over t to the sub half, okay? A lot of variables there, but n sub 0, that's just the amount you start with of an element. So amount to start. Okay, t is the time, and this is its half-life time, which you'll be given that in a problem. They'll tell you what the half-life of an element is. So the half-life of this element is 12.32 years. Okay? The textbook, I don't like what the textbook does. The textbook actually gives you a formula for each individual one I introduce. I'm like, it's probably better to know what the original one is. So the question is this, okay? Having 1 gram of this substance, I'm not even gonna try and pronounce it because I'm gonna butcher it, okay? How much will be present after 12.32 years, 24.64 years, and the last one, 36.96 years. Okay? And all we're going to do is just use that formula to figure it out. Okay? So I'll put down here n sub t, not n sub t, n of t. So what did we start with? Just 1 gram, huh? So we're going to just put a 1 there. Times a half. Now we're going to stick with what? 12.32 years divided by its half-life, which is ironically 12.32. So that's just going to be, well, let's think about it. This is a 1, right? So a half to the 1 is just half. Half times 1 is a half. So we'll have half a gram left of this element after 12.32 years. Okay, let's try another one. So the next one was 24.64 years. How much do you have left? Okay. By the way, this is an entire exponent. Okay, just like it's written up there, it's a full exponent. Now if I divide these two, I get 2. So a half raised to the second power is a 4th, times 1 is still a 4th. So 0.25 grams of this substance is left over. So as you can see, as you continue to increase the years, you're getting less and less of this radioactive substance left. So 1 times a half, it'd be 36.96 divided by 12.32. So that's going to be a 3. So a half raised to 3 times 1, 0.125 grams. So E is helping us find not only compound interest and stuff like that, but it also gives us some inspiration to find some of these other things as well. Okay, appreciate you hanging in there. I really do.